Let's examine the various processes that lead to deactivation of an excited state. Each process is in competition with fluorescence, which plays a special role since we can measure it directly. The competing processes can be divided into photochemical and photophysical processes. We will mainly be interested in photophysical processes that do not change the structure of the molecule. Photochemistry is included for completeness. Photophysics concerns mainly fluorescence, internal conversion, phosphorescence, and intersystem crossing. Absorption of a photon populates the Franck-Condon active modes of the excited state. These are the totally symmetric modes. But their population is not an equilibrium population. Therefore, following initial excitation to an excited singlet state, a molecule will undergo vibrational relaxation and perhaps even solvent reorientation to relax to a new equilibrium geometry corresponding to the excited state. A radiative decay process involves emission of a photon. Non-radiative decay involves the transfer of excess energy into vibration, rotation, and translation of surrounding molecules. The process releases heat into the surroundings. The non-radiative process that leads back to the ground state is called internal conversion. This process may be very rapid in some molecules. Such molecules are non-fluorescent. Alternatively, the fluorescence rate constant may be much greater than the non-radiative rate constant, leading to a high fluorescence yield. Fluorescence is the spontaneous emission of radiation from an excited singlet state. Absorption leads to population of Franck-Condon active vibrational modes of the excited state. These are the totally symmetric modes. Vibrational relaxation leads to a cascade down the vibrational quantum states of the excited electronic state. A new equilibrium is reached on the 100 picosecond timescale. Emission occurs from an equilibrium population of excited state vibrational levels. The fluorescence emission is shifted relative to absorption when this excited state geometry is attained. The singlet and triplet state potential surfaces may cross, and therefore a change of electron spin may occur. This is caused by spin-orbit interactions. The singlet state evolves to a triplet state. This process is known as intersystem crossing. Phosphorescence is the emission of radiation from a triplet state. Since spin-orbit coupling increases as the fourth power of the atomic number, substituent atoms such as bromine and iodine are commonly responsible for the heavy atom effect in organic molecules. Because it is spin-forbidden, the phosphorescence emission rate is very low. Consequently, phosphorescence is long-lived and has very low yield. A Jablonski diagram represents the ground and excited states, as well as transitions between them. Singlet states are denoted using S0 for ground and S1 for the excited state. Actually, that's for the first excited state. There can be S2 for the second excited state, etc. T1 is the triplet excited state. The lines represent the vibrational manifold in each state. In previous slides, these were shown in the potential energy surfaces, which are neglected as a shorthand notation in a Jablonski diagram. Straight arrows represent radiative transitions, and wavy arrows represent non-radiative transitions. Intersystem crossing and internal conversion are denoted by ISC and IC respectively. Isomerization can occur in an excited state. The molecule cis-stilbene isomerizes to the trans conformation in the excited state. The yield is not usually 100% for such processes, but they are important. Photodissociation, or photolysis, is the breaking of a chemical bond in the excited state. The excitation produces an antibonding state in this case. The potential energy surface is repulsive, as seen here. Electron transfer can be either photochemical or photophysical. If an electron is transferred to an acceptor that diffuses away from the donor, then the change may be chemical. If the charged species do not recombine, then a chemical change has indeed taken place. However, there are examples of complexes formed in the excited state that involve charge transfer, where the electron returns to the molecule, and returns both molecules in the complex to their ground states. Excimers are formed by complexes of two identical molecules after one of them is excited to its singlet state. For example, pyrene can form a cofacial dimer in the excited state. One pyrene molecule donates an electron to the other one. The charge separation results in an attraction that holds the pair together in the excited state. Then, the molecules return to the ground state and dissociate as the charge recombination process is completed. Excimer emission is associated with charge transfer. This is why excimer emission is strongly redshifted relative to monomer emission. This slide shows how the excimer emission depends on pyrene concentration. Complexation in the excited state is an equilibrium driven by the concentration of charge transfer pairs generated upon excitation. A higher concentration of pyrene in solution results in a closer average distance and therefore more efficient charge transfer. Exciplex emission occurs between two different molecules, usually a good electron donor and an acceptor. In this example, the acceptor is anthracene. When anthracene is excited, a donor such as dimethylaniline can transfer an electron to the acceptor ground state. The donor is positive and the acceptor is negative after this transfer. Here too, the Coulomb attraction holds the molecules together in the excited state. There is a redshifted exciplex emission in such systems.